Swayam Prabha. Digital India. Educated India.
Today we are going to be looking at delays and how to model them in system dynamics, what it means. So, delays exist in almost all the systems. Some delays create instability in oscillation, others filter out unwanted variability within the system, so that we can get rid of the short term variability and look at the long term performance, or remove noise from the signal. So, these are the essential aspect in all the systems. In whatever process we take, there will be some form of delay which is inherent part of all the systems. But if you just think about it in modeling perspective, delays are nothing but where the output lags behind its input by some time duration, right, whatever it may be. So, that is a very simple definition of delay. So, broadly speaking, we can think of two types of delays. One is called as a material delay, which captures a physical flow of materials. For example, if say we send in raw materials into the factory, after a time delay of say 2 days, it comes out as a finished product. As raw material comes in, maybe after 2 days it comes out as a car. So, there is a delay, and there the material is conserved. So, whatever material goes in, it either comes out as a finished product or as a scrap, right. So, there is a kind of a mass balance, or you can think of say letters that is being posted say through courier or postal service. So, whatever goes into a system then remains in transit for some duration, after end of it which it is delivered. So, those are material delays where the material gets conserved, or when you send an application for say applying for IIT, your application was a physical material, it went to the admissions office, it stayed there for some time, many different people would have processed it, and then finally you would have got some response to that, correct. So, those are also material delay. Or when you finish an exam, you give the exam papers to me, then I have to grade the papers and give it back. So, even those are also considered as material delay. So, material does not mean it has to be a physical object or anything, it can also be like an order or the exam papers, etc. So, those are also material delay. Or the act of sending an email. So, when you send an email, assume nothing is lost, but after some delay the material gets read. So, until you read it, the material is in your inbox, even after that it can go into your archives, or it continues to remain until you delete it, right. So, there also the material is conserved. So, those are all considered as part of a physical flow of materials. So, I am just having a very broad description of the physical flow. The second kind of delay is called as a perception delay or information delay, which represents gradual change in perceptions and beliefs. Even change in beliefs is going to take time. So, these kind of delays are called as perception delays, or information delays, or delays of beliefs. This is also quite interesting. Given a certain people's background, they will have certain kind of perception about things. You can't just pass a law and make it change overnight. It takes some time for it to gradually change, especially in social customs. Another more related information delay could be how you process whatever has been taught in class, right. It takes time to absorb it, if at all. At some point some amount gets absorbed, it takes some time to retain it, and over time that can also you tend to forget, So, those are called as information delay. So, there is no conservation of mass. It can't be like I taught you so much hours of material and that much hours get stored in memory. It does not happen like that, right. It is maybe some few abstract pieces of information that get stored, which also erodes or gets updated over time. Right? When you get new information, you process new information, and the old one either gets replaced or reinforced, or you just forget them. So, those kind of perceptions is what we call as information delay. Some form of both you might have seen in other courses also. Today's class we will start with the material delay, which is kind of more easy to grasp and handle. We will get a hang of that. So, material delay. So, when you look at material delay, essentially in modeling in system dynamics method, we consider two things. One is average delay time, other is distribution of deliveries or output around this mean delay. Like as I told the example of sending letters, I send letters and after a delay of say a week or a week, suppose all the letters are delivered exactly at the same time, then I know that there is a fixed delay, right. But it does not happen so. Sometimes when I post a letter today, some letters get delivered after 3 days, some after 4 days, some after 5 days, right. So, there is a distribution around this average time of delay. So, those are two things that we want for modeling the delays. What is that average time and what is the distribution around that average time that we expect, and based on that we will be choosing the kind of models we want around that. Let us take the simplest case, saying that where output lags behind its input by a fixed and a constant duration. We call that as a pipeline delay. So, whatever you send in at this end of the pipe comes out at the other end of the pipe the same quantity after fixed duration. So, it is very common in like say an assembly line kind of setup where material is sent and after a time a finished product comes out, whatever that time scale might be. An order of exit from delay is also same as order of entry, delay times are constant. So, this is one of the simplest model. So, let us do delays as a topic. Let us consider a simple pipeline delay. We represent it as, so imagine again letters being posted. So, we can consider it as material in I drew a too small box, but you can correct it, is in is your outflow average delay time D. So, we are going to be using capital D for the average delay time throughout. So, input is kind of exogenous. So, whatever it can be, material in transit is nothing but the difference of the flows. So, only equation of concern is what is this output. So, output time T is nothing but inert time T minus D. Okay. It's a very simple equation. Output lags behind input after D time periods. So, in Vensim, if you want to model it, we can't write these equations. As you might have observed in Vensim, there is no way to give a subscript of time t. Time t is taken as implicit. Correct. So, they have defined functions for that. So, if you want to model this in Vensim, out we simply model as, there is a function called as delay fixed. It takes as parameters in D time and init. That is in refers to your inflow or the input. Dt is your delay time D, delay duration, and init is the initial value of output when time is less than d, or the delay duration. So, these are two or three input parameters for this function which fully captures this. So, now internally what Vensim will do is do the same equation, output is in of t minus d, where d is your delay duration and in refers to your in here, which is same as the in here. This is a variable name, and in it is initial value. If you observe the equation, when t is less than d, it becomes negative. So, we need to know what happens when t is less than d. So, that is also specified in Vensim as what is the initial value. Typically, we take it as 0, that means there is no output until actually input starts working. So, there is a simple lag. So, if you want to write a proper equation, so this works when t is greater than or equal to d. Yeah, that is it. It is quite simple to visualize your flows. For example, if there is assume a pulse input at say time 0, at time 0 there is a pulse input, and assume there is a d equal to say 5, that means after 5 periods the entire thing is going to come out as an output. So, this becomes your out, but this pulse input is your in. It is very simple delay. So, whatever you are going to put in is going to come out. So, whatever profile it comes here, it is just going to be offset by d time units, and the same profile is going to come out after d time units for the output. So, we will look at few types of delays, then we can move to Vensim for trying it out. It is not that difficult. Look at it. So, this is what we have seen. So, this is one extreme where whatever you give after time delay starts coming out. We can take the other end of the spectrum, a kind of delay which we have already seen. Since we are looking at delay, I am introducing it as a first order material delay. What you are saying is, in this case output is proportional to the stock. So, assume that whatever inflow occurs, the stock is mixed perfectly. The analogy here is again the same water tank. So, in this water tank, as you can see, there is inflow happen, and suppose there is a tap below. It is not, water is not going to follow first in first out policy. As soon as it comes, it is going to be assume there is also a mixer which keeps mixing it. So, water is going to just come out almost instantaneously. As long as inflow started, immediately outflows will also start, and tank will continue to drain in this model. This is nothing but a simple first order model that we already seen. You know, when there is a outflow which is proportional to the inflow and stock in hand, so tank is going to keep draining until the entire tank is drained, right. So, that simple first order negative feedback system is also called as a first order material delay. We will do the Vensim one, and couple of questions we can think about. If it is a first order material, like a first order negative feedback system, so whatever inflow occurs and the system starts draining almost instantaneously. So, what time does the maximum value of stock occur? Will be at time 0, will be at the initial point. How long on an average it spends?